And so this is due 2 weeks from tomorrow. And not surprisingly, it's on binary trees. So same idea as what you've been doing in your other assignments. You're going to create a command interface that the user can type simple commands with in order to build and examine and manipulate a data structure internally. In this case, the data structure is a binary search tree. So a limited set of commands. The S command lets you search for a number that you've inserted. You can say search 10, and it should tell you if the number 10 is in the tree or not. Okay, you can say delete a number, delete 10, D10, and it should remove that number if it's in the tree. If it's not in the tree, give the user an error message, keep going. So most of the action happens with this uppercase X command. Okay, X asks you to examine the tree, and you're going to print out a bunch of different information about the tree, starting with 3 depth-first traversals in order, pre-order, and post-order. Sorry, pre, in, and post. So node left, node right, and left, right node. So when the user gives the X command, you print out NLR colon, and then a comma-separated list on the same line of the node values, and then a new line. I'm going to be picky about syntax, about format on this assignment. Okay? Not that it's a big deal if you print out 1 number per line or if you print some other stuff, but I want to make sure before you leave Clark that you're able to take a specification and follow it, so that if you get to UW or WSU somewhere and you're asked to do this and you do something different, you don't lose points. So it's spelled out here in detail, okay? Print out the numbers on 1 line for each of these traversal orders, okay, separated by commas. So NLR colon, list of nodes, LNR colon, list of nodes, LRN colon, list of nodes, 3 lines. Then you're going to do a breadth first search. BFS colon and a list of the nodes in breadth first order. Then you're going to calculate the height of the tree and print that out. So height colon followed by a number that corresponds to the height of the tree. And then you're going to check whether the tree is balanced. And you're going to say balanced colon and say either yes or no. All right, question mark shows you a list of valid commands. Q exits the program. Capital Q. I don't care if you exit on a lowercase q. That's fine, but make sure that it does at least these things. Okay, if you just type in a number, just like with the list assignment, just like with the stack and queue assignment, if you just type in a number, that gets added to your tree. And it's a binary search tree, so you have to add it in the right place in the tree. And you're only allowed to have a number in the tree once. So if you're asked to enter a number, check first, make sure the number is not already in there. And if it is, give a message saying that's already in the tree. So let's see what this looks like. So suppose you type in the numbers 20, and then 10, and 30, and then you say X. Okay, when you type in a 20 with an initially empty tree, that's going to have to become the root. When you type in a 10, it's going to go to the left of the root. There's nothing there. That's where it'll put the 10. When you type in a 30, it will go to the right of the root, find nothing, and it'll put the 30 right there. So this is the tree that should be built internally if you type in 20, 10, 30. Okay, now when you say X, you're going to traverse it a number of different ways. The first is node left, right, pre-order. Pre-order traversal means first visit the root, so print out a 20, and then do a pre-order traversal of the left tree, and then a pre-order traversal of the right tree. So how do we traverse a tree containing just a 10? Well, print out the root, and then we traverse its children, but its children are null, so there's nothing else to do. And to traverse the 30, we print out the root, and then traverse the null left and right children, which doesn't do anything. The in-order traversal is just a different ordering. Bless you. Do an in-order traversal of the left subtree, then print the root, then do an in-order traversal of the right subtree. So traversing the left will give us 10, the root is 20, the right is 30. And this should always come out in order. If you're building your tree correctly and you're traversing correctly, the in-order traversal will be in order. Okay, that's a quick first level check to see if your code's doing the right thing. And then post-order is again just flipping around the order of these things. Traverse the left and right subtrees first, then print the root. So here we'd get 10, 30, and 20. And then the breadth first search, which we're going to go over all of this. Breadth first search basically begins at the root and then moves down and prints out all the nodes that are one level deeper from left to right, and then moves down and prints out all the nodes that are one level deeper than that from left to right, and so on. So this would be a 20 and a 10 and a 30. That's another quick way to see if there's a big problem with your tree, because if you're doing a good BFS, it's pretty easy to tell what the order should be just from looking at a picture of the tree. You basically just move from left to right and slowly go down to deeper levels. But having this correct doesn't guarantee the tree's exactly right. All right, then you're going to look at the height. So what's the height of a tree mean? Depth of the deepest node, right? Okay, what's the depth of a node? Distance from root. So this has a distance of 1 from the root. You have to go through 1 hop. So the depth is equal to 1. This has a depth of 1. The root takes no hops to get to there from the root, so that has a distance of 0. So the maximum depth is 1. That's the height of the tree. And is it balanced? Yes, because it's nicely balanced. And then you can go ahead and you can insert some more nodes, you can delete some nodes, and so on and so forth. And the code should just keep doing its thing, keep building a tree, keep showing you what you've got. All right, so here's my code. So you can print a question mark for a help message. I don't know if I have a Q command. Yeah, I do. Good. I didn't put it in the help. All right, so let's build our tree. So we'll put in a 20, and we'll put in a 10, and we'll put in a 30. And if we say X, that should be all the information about our tree. So left node right node, node left right, breadth first search, height, and balanced. That all looks good to me.
The height starts from 0.
Say what?
Height starts from 0.
The height of a tree containing just a root is 0. That's a definition. What's the height of an empty tree? -1. So if there's nothing in the tree, the height's -1. If it's a single node, the height is 0. So try those edge cases, right? Do your X on an empty tree, and I forgot a return after the breadth first search for some reason. But all the traversals should be empty, height should be -1, and it's balanced. And if I add a single node, right, all my traversals give me the same thing, which is just the root. The height is 0, and it's balanced. So this is going to be a pretty unbalanced tree, because it's going to look like this. Do not balance the tree. So node left right node, right, give you that information. The breadth first search is clearly just moving down, so it's giving our stuff in order. And the height is 1, 2, 3, 4, 5 hops, right? Depth of 5 on this node, that's the height of the tree, and definitely not balanced. And you should be able to delete nodes. So I can delete 103, and you can't actually see the tree, but you can tell from this that it's going to have the correct order. All right, so try your edge cases. All right, so I'm back down to a single node. Delete that node, make sure it doesn't blow up. Delete nodes that don't exist, search for nodes that don't exist. Search for nodes that do exist. Search for the first node, search for a leaf node. Make sure you can delete the root, and so on. All right, so details. Details. First detail, do not balance the tree. Okay, if you balance the tree, your numbers are going to come out looking totally wacky to me. And I'm going to have to go into your code and dig around, and I'm probably going to have to rip out the balance code so I can test the rest of the code and all kinds of things like that. So don't balance the tree. Use the search algorithm that we've talked about, that we're going to talk about again as we go through the details of this. But basically, to insert into a tree, start at the root, keep moving to the left or the right until you get to a leaf, and then put it in the right spot. When deleting a node, your algorithm for deleting the root of the tree is to take the largest node from the left subtree, move that to the root. Okay, don't copy the value, move the actual node, which means since you're deleting the root, the left child is going to adopt the root's old right child. Okay, so take the root out, take the thing that was on its right, give that to the biggest node on the left, and make that the root. All right, the one exception to the deleting rule is if there is no left subtree, then just move the root down. So if you've got something like this, right, so there's your tree. You want to delete the root. Get rid of the root. Find the largest node in the left subtree. That's a 9. Put the 9 up here. Got to do it on the left. Yeah. Again, because that's what I'm going to be looking for. I'm going to make some sample trees, and I'm going to try some things, and I'm going to look at your code and see what it does. And if your tree ends up looking different, then I got to dig into it and see if it's doing the right thing in the wrong way. All right, so to delete the root, find the largest node in the left subtree, move it up to the root. Something's bothering me about that. Oh, yeah, okay. And if this thing has a left subtree, hang it off the 8. All right, if there is nothing on the left, so if we want to delete the 9, there's no left subtree to work with, just change your root to the right subchild. Okay, so that's the easy way to delete a root if there's nothing on the left. And you got to do it that way. Don't take the smallest thing from the right and put that into the root. That'll work. That's a valid delete, but it's not what the assignment's asking for. All right. Make sure you free all the memory that you allocate. Use valgrind. Make sure you got no memory leaks. So same as what you've been doing, when you delete a node, you also need to free the memory associated with it. And when you're done with the program, when you get the X command, the Q command, you want to go through and visit each node and free its memory behind you. So make a free all nodes function that basically does a traversal, whatever order you like, but each time it visits a node, releases its memory. All right, breadth first search, you're going to have to use a queue. The algorithm for doing a BFS involves a queue. Depth first searches involve a stack, and we're writing these recursively, so we're basically using the system stack to manage the memory. But a breadth first search we're going to have to do ourselves. It's not going to be recursive, it's going to be iterative, but we're going to have to use a queue to do all the housekeeping. So keep your queue code from PA3, and the only change you're going to have to make to it is that we need a queue of tree nodes instead of a queue of integers. And we'll run through that algorithm in a little bit. But so you get to reuse your queue code. All right, so those are all the details, right? Put everything in a directory, make a makefile. That'll give you an executable. Call your executable PA4. Put it all together into a tar file, upload to Canvas. So suggestions. The first two functions that you probably want to write are inserting into a tree and doing an in-order traversal. Okay, why? In-order traversal tells you if you're inserting correctly because your numbers should come out in increasing order. And it lets you see the numbers that are in the tree. So if you do that and you're seeing crazy negative billion numbers, you know something's wrong with insert. And if you want to do your traversal first, you can build trees by hand. Okay, you did this in some ODPs. You can just make a tree node, give it a data value, make some more nodes, point to it from the root, and sort of build up a small tree by hand, and then pass it to your traverse routine and see if it's going through the structure correctly. So you can do traversal first if you like, but then do your insert routine. And all of these routines, other than breadth first search, are going to be recursive. And I'd like you to code them recursively. Okay, that's part of the assignment. So we'll go through these in detail. But inserting into a tree, basically, if the tree is empty, put it at the root and you're done. Otherwise, if it's bigger than the root, just insert it into the right subtree using the insert routine. If it's smaller than the root, insert it into the left subtree using the insert routine. So most of these, once you get it set up, once you have a T node, once you understand how to deal with null roots, most of these routines are a few lines of code. Okay, but getting to those few lines of code, that's the challenge of this assignment. And you want to make sure you understand why those few lines of code work. If you take pseudocode that we do in class and you write code trial and error until it works, right, you may not actually understand how the recursion is getting you the answer that you want. So you really want to make sure that you understand this and ask questions if you think you don't. Because once it clicks, then you've opened the door on a whole bunch of possibilities. All right, so insertion and traversal first. Deletion is probably the hardest part. It's got lots of edge cases. It's a combination of recursive and non-recursive, and it's just kind of a big, ugly thing that tends to break code. So I would leave deletion for later. Once you have in-order traversal, the other traversals that are depth first are pretty straightforward. Search is no harder than traversing. Insert will be done first. Height and balance are nice recursive functions, and they take almost no work. Okay, as long as you understand the definitions. So the second hardest part is going to be the breadth first traversal. And that's going to involve a queue, and like I say, you have to modify your queue so that it actually stores T nodes. So we'll go over that in a minute. And then deletion is the worst. I mean the most fun. So probably leave that for last unless you feel like taking it on earlier. And definitely, right, you want to be snapshotting your code at this point. Ideally using something like Git, but some form of snapshotting, because this is going to be a big program when it's all finished. And it's not uncommon that you start writing your delete code and it starts breaking things. And sometimes it breaks something and you think it broke your add function, you start changing your add function, and now you've like taken some steps backwards. It's possible you'll delete a node and you won't get a seg fault when you say delete, but it'll leave little time bombs in your data structures. And a few steps later, you'll try to search for something and all of a sudden it seg faults or hangs and never comes back. So keep snapshotting versions of your code, get into really, really good programming habits, keep documenting, right? Document inside the program, write yourself readmes if you need to, keep a journal of what you're doing and what you're working on, whatever's going to work for you, but be developing these habits as you work on these assignments. This is a really good one because it's a fairly ambitious assignment. All right, good. So yeah, my version was 276 lines, and most of that's code, not comments. All right, questions, concerns? So tomorrow, right, come in if you want to work on any of this stuff, right? If you don't finish nailing down PA3 and you want to go over how close you got or what you didn't get to work, do it tomorrow. Mostly Fridays I'm up here doing my own thing and talking to one or two people, so take advantage of it. And there's no class Monday. Monday's a holiday, so no classes here. All right, let's talk about breadth first search. So we've got a tree. Let's say it looks like this. And the idea is we want to print out the nodes on the highest level first, the root A, and then we want to come down to the second level and print out the B and C, and then the D, E, F, and the G and the H. And it's hard to do this recursively. The problem is at each level, we potentially have twice as many children that we need to print out, and the number of things we need to remember is growing. Let's add one more child over here. Make it more interesting. So here's an algorithm for doing breadth first traversal with a queue. Okay, so step one, add the root. So insert the root into your queue. Let me write this with code. All right, so insert the root. And then we're going to begin an iterative process. So if queue is empty, then we're done. Otherwise, temp equals whatever's at the head of the queue. So remove the head of the queue, stick that in a temporary node called temp. Print out temp's data, so that's our actual visitation of that node. And then a pair of conditionals. If temp left is not null, insert it into the queue. And if temp right is not null, insert that into the queue. And there's the evil goto statement. Go back to step 2. So put this in a while loop, right? So start the whole process by inserting the root into the queue, and then we just loop on this until the queue is empty. Remove the head of the queue, print out its data, push its left and right children into the queue if they're not null, and go to the top and just keep doing this. So let's see what this does. So here's our queue. Here's the head, and here's the tail. Here's what's being output. So I'll record everything that's printed. And we have one temporary variable called temp, which doesn't have any initial value. All right, so step 1, we seed the whole process by inserting the root into the queue. So A goes into the queue. And this is a tree node, right? So A itself has a piece of data. It's got a left child and a right child that are both pointers to T nodes. Data is probably an int. So your queue is going to be a linked list where the data piece is actually a pointer to a T node. So your queue node is going to contain a pointer to a tree node, a pointer to a queue node, and a tail pointer to a queue node. All right, so we got data structures inside data structures now. All right, so we do step 1, we inserted the root. Check to see if the queue is empty, it's not. Remove whatever at the head of the queue, save that in temp. So temp is equal to the node A. Print out its data, so that's whatever A's data is. And then if temp left is not null, insert that into the queue. Well, temp left is equal to B, so we'll insert that to the queue. And then temp right is C, that's not null, we'll insert that into the queue. And we go back up to the top of our loop. Queue is not empty, remove the head of the queue, that's B, that's our new value for temp. Print out its data. And I'm printing a comma before each thing except for the first one. And then if temp left is not null, well, B's left child is D, that's not null. Push that onto the queue. If temp's right is not null, well, B's right child is null, so there's nothing to push there. Go back to step 2. Queue's not empty, remove the head of the queue, that's a C. Print out its data. Push its left child into the queue, that's an E. Add its right child into the queue, that's an F. Go back to the top. And you can see what's happening here. We just added some things that are at the next level down, but they're not going to get processed until the things that were already in the queue are taken care of. So we're going to remove the D. We're going to print its data value. It has no left child to add. It has no right child to add. So we're just going to go back to step 2. We're going to pull out the E. That becomes the new temp. It has no left child, it has a right child of G, so we'll put G into the queue. And then we're going to pull out the head of the queue is F, that's the value of temp. We're going to print that node's data value. And then we're going to take its left child and its right child, insert those into the queue. And this first in, first out is what's forcing us to do everything that's happening at one level before we do any of the stuff that we just added while we were processing this level. Right? When we process this, we're printing out these values. We're also adding these values into the queue, but we're not going to do anything with those until we've pulled all of these things out. That's what's getting us to go down one level at a time. So we can finish this up. Back to step 2, pull out the G, that's our value of temp. Print its data value. It has no left or right children, nothing gets added. Pull out the H, that's our value of temp. Print out its data value, no children. Pull out the I, that's our temp value. Print out its data value, no left or right children. We go back to step 2. the queue is empty, we're done with the traversal. And our output was the nodes in the expected order. So to me, breadth first search is fun. It's a fun algorithm to put together because you're doing data structures inside data structures. Right? You've got a list that's implementing a queue that's being used to store pointers to tree nodes. How much more fun can you have? And when you get it to work, it's really clear that it's doing the right thing, because you build up a tree on paper and you see what it looks like, and then you do the BFS and you just get a nice scan of each level of the tree. And this is also a handy way to print trees because it goes from top to bottom. And so if you don't want to save your nodes in memory, all you got to do is figure out how far over to move things. So figure out the height ahead of time or something, and then just visit these nodes in order and print them out in the right place. It's a lot harder than that, but it gets you there. All right, does that make sense? It's a first or second pass, so it may be fuzzy. But that's the essential algorithm. All right, so questions on hashes. Yeah.
So I think I remember somewhere, is there like a name for data storage type? Is it just hash?
It's a hash, or sometimes it's called an associative memory, but usually it's called a hash. So what does a hash look like abstractly? There's some kind of initialization. There's our store, key and data. There's a fetch. There's a delete. And there's some sort of iterator, some way to go through and pull all of your information out. And usually that's done in a way that lets you do something with the nodes one at a time, like a get first key and get next key. But for now, let's just imagine there's a print, which just goes through and dumps everything that's in the hash out to standard out. It's not terribly useful. It's more useful to have something that gives you keys. But just for sketching out some code, let's just think of these. So this would be the interface that the user would have for working with this structure. And we might implement it underneath with an array, like we've been doing. We might use some other kind of structure. We might have a piece of hardware that actually is an associative memory, maybe built with memristors or something bizarre, and we're just tying into that, right? But the interface would be uniform. So let's look at implementing this with an array. So we've got hash functions, right? We have some kind of hash with some key and a probe, and this gives us an index into our array. And so our array, which is the actual hash table, looks something like this. So index 0, 1, 2, and so on, up to n minus 1. So this is a hash table that can hold n unique values. And we need some information. So when we store information in an array, we can't just write numbers into an array and then hand someone our array and say, here's my set of numbers, add them up for me. What else do we need with just a straight array of integers? if you're going to write a function that takes an array of integers and adds them up and returns the sum, you need something more than just the array of integers. You need the length. You got to know how many things are in that array. Because all you're getting is the address of the first element. That's it in C. And you can just start looking at successive locations, and you're going to see something in there which is an integer. But is it part of the array or not? I don't know. And maybe this array was declared to hold 1,000 integers, but you're only using the first 7 of them. So you got to have the size. With a hash, the size doesn't work for, because we're not storing things in this hash successively. They're going to be bounced all around by this hash function. So in addition to storing our data, we also need to know whether that data is valid or in use. So our valid flags would initially be set to zeros. And now when we want to store something, we hash it with a probe of 0. We find the index. We look at that location and we say, is there something already in this location? And if there's not, we can store our data there and change the valid flag to a 1. So let's use a really rudimentary hash function. So hash of n comma p is just going to be n plus p squared mod 10. So let's store the number 11. So we'll try a probe of 0. We'll hash 11, 0. That gives us 11 mod 10 is 1. And this was a 0 saying there's nothing in there. So we'll store our data here, and we'll set our valid flag to 1. Now we want to store a 21, and that would hash to the same location 11, but there's already something occupied there, so we need to rehash. So we can start sketching some code. So storing a piece of data with a key. Start off with a probe of 0. Location equals hash key comma probe. And let's just call this whole thing our H table. So if H table bracket location dot valid is a 1, it means that location is occupied. So increment the probe. Go back up here. So rehash with our second probe value. So in this case, we'll set our probe to 1. We'll calculate 21 plus 1 squared is 22. Modulo 10 is 2. That's valid. That valid flag is 0. So our 21 will get stored here. So once we come out of this loop, then we'll just say H table bracket location dot data equals data. So that's a find store algorithm. And this is basically looking for a location, but we've got to be careful here, because make sure you're not stuck in an infinite loop. Because if the table's full, or if our hash function is not ideally chosen, we might just keep bouncing around between certain values that are all in use. And we're never going to find a place to store our data. We need to detect that somehow. So we can do it by counting the number of times that we've iterated, or by making sure we don't come back to a location we've already seen. And there's different techniques, but you got to do something. So storing, initialize a probe to 0, hash your key with that probe, see if that location is available in the table. If it is, store it in the table and set its valid flag. If not, bump up your probe, rehash, try it again. All right, so 21 gets stored here, and if we want to store 32, same thing is going to happen. It'll collide here. We'll hash with a probe of 1. That'll come out to a 3. We'll store 33 here. That'll be a 1. So the trickier part is deletion. So delete 11. Well, we can hash our key. So set your probe equal to 0. Hash your key with that probe. So we also have to store keys in here. But hash your key, look in the table, see if you find the thing that you're trying to delete. Okay? If you do, then you go ahead and you clear the valid flag. But we also need to remember that we deleted it. Because if all we do is clear the valid flag, then when we try to look for a 21, we're going to take a 21, we're going to hash it to an 11, we're going to look in here and say it's not equal to 21 and that location is not in use. I guess 21 is not in the table. So when you delete, you clear the valid flag, but you need to remember that what was in there might have caused a collision, and so you need to mark a flag saying this has been deleted. And when we search for something, if we don't find it in an entry, but we find that it was either in use or it was deleted, we need to keep rehashing. Bump up the probe, hash again. So we'll bump a probe to 1, we'll rehash to location 2, we'll find our 21 there.
Could you use like a third valid flag that just says
Yeah, so you can use a single flag and have 0 for not in use, 1 for in use, and -1 for deleted. That would be good. So this complicates the algorithms a little bit, but they're not that complex. It's just details, right? So when you go to store something, same deal. Hash to a location, see if it's in use. If it's not, you can go ahead and store it right away. It doesn't matter if it was deleted or not. Go ahead and store it, mark the valid flag, get rid of the deleted flag. When you search for something, if it's not found at this location but it was deleted, go ahead and rehash and search again. When you search for something, if it's not at this location, keep going, but if you search for something and it's an empty location and it was never deleted, then your search is done and you didn't find your number in the table. And then a print is a pretty easy routine. Just march through, and every time that you find a valid flag, print out that piece of data or return that key if you're making an iterator. So working with a hash, right, creating these routines is really no harder than stuff we did in 224. It's not dynamic memory in the sense of linked lists and trees, right? But the algorithms they have some subtleties in them. So we may do some ODPs next week, getting deeper into this kind of structure. We'll see. All right, so tomorrow is Friday, Monday's a holiday, Tuesday is the next time we get together. So Tuesday, we will start going through tree manipulations in more detail. We'll go through some pseudocode for the different operations that you'll have to do, and then ultimately we're going to move on to talking about balanced trees. So that'll be the end of our tree discussion, and that's week 7 already. So we got 3 weeks after that, and we're done. All right. I will see you next time then.